Hello, welcome back to Dinosaurs. We're going to keep walking through Module 3, the Ceriscia. Today we're going to talk about the Ceratosauria, and then we're just going to keep on going through. So before we do that though, some announcements. You can email me, post on the discussion board. There's a lot of different ways to get a hold of me, so don't feel like you're alone in this. All right, so let's review what we talked about last time. So which of the following is New York State's official dinosaur? So we do have an official dinosaur. We also have an official state fossil, which is not a dinosaur. It's Eurypterus rhomipes, the sea scorpion. So which of these is our official dinosaur, though? All right, let's see. It is. So Coelophysis is New York State's official dinosaur, known only really from the tracks in here. Sometimes you'll see them referred to as Growlator. That's the name for the print, that kind of three-toed print that was probably Coelophysis. But again, one of the problems with trace fossils is that we don't always know who made the tracks. These are probably Coelophysis tracks, but we don't know. So a lot of times they'll give the ichno genus, the trace fossil itself, a different name. So the print is called Growlator, but it was probably made by the dinosaur known as Coelophysis, probably. And that's our New York State dinosaur. And we certainly see material in other areas around New York, but not in New York itself, only the prints. Why were the basal Triassic dinosaurs relatively small and less diverse than their Jurassic and Cretaceous counterparts that would follow? So take a look at that list. Also take a look at the picture there, because there's a hint there. Okay, so here's Coelophysis. Some Coelophysis here roaming around in the background. Again, remember, sometimes they were found fossilized in groups, so they probably did have sort of a pack or herd community social structure. How well they communicated and coordinated, we obviously don't know, but they did appear to at least temporarily group up. But they were competing in this environment with the phytosaurs, the kind of crocodile, alligator-like crocodilomorphs. They're competing with the Rawasuchians, these big apex predators. And they were competing with Adasaurs, the large herbivorous crocodilomorphs. And so there was a lot of competition for resources in the Triassic, and dinosaurs weren't winning the competition. They were behind. And so only at the end of the Triassic, when these other things went extinct, did dinosaurs really grow and diversify to fill those niches. Okay, so let's just walk through the cladograms again. So last time we talked about the basal Triassic Ceriscians, and today we're going to move on to the true theropods. And these are so this is the Theropoda cladogram. Last time we also talked about Coelophysoidea and Alephrosaurus. Today we're going to kind of march up this branch, the Ceratosauria. So we're going to talk about Ceratosauridae and then kind of walk all the way up through Abelisauridae. And so we're going to talk about some examples of each of these groups. And then we're going to kind of talk about this group next time, and then this group, and then this group. So we're going to kind of keep walking up this cladogram, and you see the different morphology features that define these branching points on the cladogram. I'll mention those, but you don't really need to remember those. It's just that's a little bit higher detail than we need for this particular class. But so let's talk about the Ceratosauria. So Ceratosauria means horned lizard. So rhinoceros, the modern rhinoceros, cer means horn, cer is horn. So Ceratosauria is horned lizard. Rhinoceros is nose horn. So these horned lizards, and why they're called that is because they have these highly ornamented skulls. Well, maybe not highly, but you see this one has one kind of nose horn. Here's the dual horns above the eyes. Here you see kind of like a more suppressed crest here, and then a little bit of crest here. This kind of like waddle in here is like soft tissue. That's probably pretty speculative, but so the Ceratosauria as a group, they first appear in the early Jurassic. So last time we talked about these basal Triassic theropod ancestors. These are the first kind of true theropods, and they don't appear until the Jurassic. So by the time these appear on the scene, the Rawasuchians, the Phytosaurs, the Adasaurs, those are all out of the way. So they've gone extinct at the end Triassic extinction. And Ceratosaurs are one of the first that kind of radiate out into those now unfilled niches. So they make their appearance in the very early Jurassic, and they make it all the way through to the very end of the dinosaurs. There are Ceratosaurs still alive at the very end as the meteor falls out of the sky. So they're still around to the bitter end. Unlike the dinosaurs that we've talked about earlier, Coelophysis, Dilophosaur, all those other basal ones, they don't even really make it through to the Triassic or through the Triassic. So Ceratosaurs are the dominant carnivores in Gondwana. We haven't really used, well, I mentioned it I think a couple times, but we have Pangea assembled. Gondwana are the southern continents of Pangea, and I'll show you a map on a couple slides later. And the North American continent, European, and Asia, Laurentia or Laurasia, are the northern continents together. So Ceratosauria are dominant in Gondwana, but they're much less significant in North America in the Jurassic, and then they don't make it into the Cretaceous of North America at all. So by the time we get to the Cretaceous in North America, they're just gone from North America, but they do continue on the southern continent. So they're still around in South America, and probably Africa, and there's little evidence in Australia and Antarctica, but they're probably there as well. At least we kind of make that assumption. So obviously what defines them is that the horn, the ornamented skull, but they also have a very prominently reduced forelimb, kind of less so here, but you see some of the more derived forms, the arms are very limited, they're very reduced, but unlike T-Rex and some of the other later, more derived, more advanced theropods, they don't actually have a loss of the digits, so they still retain all of the fingers, the 4 fingers that they have at this time. So even though the arms are reduced in size, the hands are still there. And we'll see the different shapes and sizes that they come in here. This is just kind of a branching tree of the family here, and we'll be talking about some of these as we go through the lecture. So the first one that we're going to talk about, so Berberosaurus. So it means Berber lizard. So remember, saurus is lizard. Every time you see saurus, it's just lizard. So Berberosaurus is Berber lizard, after the Berber peoples of North Africa, like Morocco, Algeria, Liberia. They represent the oldest known ceratosaur. And they're so old, so basal, they're kind of at the very beginning of the Jurassic here, that they were maybe previously assigned with the Dilophosauridae, because they're sort of transitional. So they're kind of stuck in between this transition between kind of the Triassic basal Saurischia that we talked about last time, and kind of starting to move up the cladogram into the more advanced, more derived groups. These are kind of transitional between there. The other problem is that there's really only fragmentary remains of this particular genus, but they were probably comparable in size to some of the larger Dilophosaurs. So remember, Dilophosaur was probably the first like truly apex predator dinosaur, where dinosaurs were finally like at the top of the food chain and able to eat pretty much anything else. And if you saw one, it would be kind of a little bit bigger than you, not towering over you like T-Rex, but slightly bigger than you, and it would be very dangerous and you wouldn't want to mess with it. You see here is a dog for scale. Not sure what kind of dog, looks kind of like a lab. But you can see that, you know, this thing is on the order of like as tall as a person to a little bit shorter. And so it's a pretty big dinosaur. I certainly wouldn't want to mess with it, but it's definitely not as large as these things are going to get. Again, it's kind of this transition from these kind of smaller forms in the Triassic. And then as we get into the Jurassic, the competition's out of the way. The dinosaurs are filling this apex predator role. They're starting to fill the apex herbivore role, and the herbivores are getting bigger, the herbivorous dinosaurs are getting bigger, and the carnivorous dinosaurs get bigger in response. and the herbivorous dinosaurs get bigger and the carnivorous dinosaurs get bigger in response. And so there's this predator-prey arms race, and it's just kind of getting kicked into gear in the Jurassic here. And so the Berberosaurus is kind of this initial step in this direction. Saltrio Venator, it translates to Saltrio hunter. So Venator means hunter, and Saltrio is an area in Italy. You'll see this Venator suffix quite a lot on some of the other theropod dinosaurs, because remember, they're almost exclusively carnivorous dinosaurs, so they're hunting their prey, they're feeding on other animals, in a lot of cases feeding on other dinosaurs. So it was a marble quarry in Saltrio, Italy, where the specimen was found. So remember that all dinosaurs, with the possible exception of Spinosaurus, which we're going to talk about, I think, on Monday, all dinosaurs are terrestrial. And limestone and marble is kind of a marine rock. So limestone and marble, limestone is formed from the skeletons of marine animals that make their shells out of calcium carbonate. And so it's kind of odd to find a terrestrial dinosaur in a marine environment. So this was found alongside like ammonites, the little floating squiddy things that are, you know, very similar to like the nautilus of today, crinoids, the sea lilies. This specimen was found alongside marine fossils. So if it's a terrestrial animal that lives on the land, how did it get out here in the marine environment? Well, one way that this generally happens is the old bloat and float. So the dinosaur died either kind of at the beach and was washed into the waves and kind of floated out to sea, or it died near a river and was kind of transported. But when an animal dies, the internal parts start decaying and it generates gases, and those gases are trapped. And so if you see roadkill, you'll often see them kind of stuck with their feet up in the air, kind of bloated and swollen. Sometimes they even pop, which is kind of gross. But at that point, they're actually buoyant and they would float in the water, and they do carry out to sea. And when it pops, it sinks and it's left over in the marine environment. So this thing wasn't living in the marine environment, or at least there's no evidence that it was. There's no marine adaptations here. But it was found in marine rocks because it died and it floated out there. It's probably the oldest kind of truly large-bodied theropod. So you see, here's a human here for scale. You see the specimen in the background. You also see how limited the fossil evidence is here. So this was an active marble quarry, and they actually blasted with dynamite, and that revealed the bones, but the damage had already kind of been done. They basically exploded part of the skeleton, and they had to sort of reassemble the pieces. And even still, most of the pieces weren't there. So one very common thing with the bloat and float is that pieces don't all make it to the end. Stuff gets scavenged, stuff kind of falls off. Yeah, I know, gross. Taphonomy happens. Remember, taphonomy is everything that happens from the time an organism dies all the way until it makes it into a museum collection and gets analyzed. There's a lot of things that can happen, a lot of changes that don't help the preservation of the specimen along the way. But if you reconstruct from some of these bones, and again, this is tricky, but we generally know the shapes of dinosaurs and how they're generally put together, and we know the general ratios. And so if you only have a few scattered bones, you can make educated estimates of the rest of the animal and try to kind of reconstruct the rest of the morphology. But again, there's big error bars on that. The more material you have, the more comfortable you are. The more specimens you have, the more comfortable you are. But it's not impossible to reconstruct from relatively limited evidence, based on what we know from specimens that are closely related and more complete. But you see, this is kind of a day in the life of Saltrio Venator, kind of taking a stroll on the beach. Maybe this is the beach where it keeled over and got washed out to sea, but you see these crocodilomorphs here. So these are crocodile members that are related to the Rawasuchians, but remember, the Rawasuchians themselves have gone extinct. The kind of smaller crocodilomorphs, they're a little bit long-legged, a little bit more erect than we think of crocodiles today. But you see here the tables have sort of turned. These things are small and scurrying around, kind of scavenging on whatever washes up on the beach. And now the dinosaurs have taken over the top spot. They are the apex predators here. You see the prominent horn here on the front, very typical of the Ceratosauria, and you also see the kind of reduced forelimbs, although not as reduced as we're going to see ultimately. The fingers are not quite reduced yet either, as in the more derived Ceratosaurs. So I guess also I should mention, so Venator, the hunter thing, it was also a kind of gladiator in ancient Rome. Primarily they were gladiators that fought wild animals as opposed to other people. So it was a special type of gladiator, and that, again, that's where the name comes from, hunter or gladiator. So now on to Ceratosaurus itself. So this is the specimen for which this entire family is named. And again, it means horned lizard. And it's very clear as to why. You can see this nice prominent nose horn here on Ceratosaurus itself. And it was first described in North America by our good buddy Marsh. So remembering back to the Bone Wars feud, this is kind of towards the end of the Bone Wars. It's kind of not the golden age of the Bone Wars when everything was fast and furious. At this point, they were getting a little bit older and a little bit burnt out and probably sick of fighting each other for decades. But this was kind of named from North American material, but no other specimens were found in North America until the 1960s. So that kind of 80-year gap there gives you some indication of just these things weren't very common in North America. They weren't a very large portion of the ecosystem. And so one reason why is, again, think back to the whole competition angle. Rawasuchians outcompeted the dinosaurs back in the Triassic. Now large carnivorous dinosaurs are competing with each other, with other large carnivorous dinosaurs. This is a picture here of several dinosaurs, not all of them. There was a large sauropod dinosaur population as well that's not shown here. But there are several much larger carnivorous dinosaurs in this environment, most commonly Allosaurus. So Allosaurus isn't the largest in this environment, but it's by far the most common. It makes up about 75% of the larger carnivore specimens that we find in the Morrison Formation of Western North America. And you see here, here's Ceratosaurus. Looking at the body size comparison, it's just not even close. It's about half the size of the Allosaurus. Some of these larger individuals, Torvosaurus, where we'll talk about these later on in the class, they're much larger, but also much less numerous. But again, Ceratosaurus, this is in North America in the Morrison Formation. There's also some isolated material that is speculatively Ceratosaurus. It may not in fact be, but there's also some evidence that they're in Africa and also maybe into Europe. So these are places that ceratosaurs usually aren't. So these are some of the northernmost continents, and then Africa doesn't really have a lot of them either. So Ceratosaur was kind of going places that these Ceratosauria don't usually go. But you see here again, size comparison, it's still a pretty large dinosaur. This man is quite stylish here with his top hat and cane for size comparison. You wouldn't want to mess with it for sure. You definitely wouldn't want to encounter it. But compared to Allosaurus and some of the largers, it just couldn't really keep up. It probably wasn't actually capable of taking down some of the very large sauropod dinosaurs like Allosaurus, and the larger ones could. So speaking of relatively small, some other forms here, Alephrosaurus. Alephrosaurus means light-footed lizard. You can see that it's kind of a much more slender build, and it looks like it was built for speed and agility. It's going the distance, it's going for speed. Alephrosaurus is kind of a lot different than some of these other ceratosaurs that we will see throughout the rest of today. Not really a very similar body plan at all. Much more, again, slender and kind of structured for speed and hunting and quickness versus being a bulky carnivore. It actually looks a lot more like kind of the earlier coelophysids, and so originally it was actually assigned with coelophysids, and that would have been a little bit weird because again, coelophysids, they were saying like went extinct at the kind of the end of the Triassic. So this would make these like Jurassic coelophysids that would have survived through that. And later on with some genetic evidence, or phylogenetic evidence, I should say, it's been kind of reevaluated and they've been put in with the Ceratosaurs. You see they don't have, or at least this reconstruction and this reconstruction don't have the prominent kind of horn. So the horned lizard doesn't really apply here, but you see that they do have the reduced forelimbs, the reduced arms, without the missing fingers, as you'll see in the other theropods. So why are they so different? Well, whenever something like this arises, you have to ask yourself, so what would make an animal be kind of more slender and smaller body size? So one is responding to climate. So if it was like a warmer, drier climate, I should say hotter, drier climate, these adaptations would be more favorable. It also could be in response to the diet. So their teeth structure, their body structure, it indicates that, well, first of all, they weren't even capable of taking on some of the larger herbivorous dinosaurs. And if you look closely at the teeth structure, there is some evidence that maybe they were omnivores or possibly even herbivores. So they were maybe eating something different, and so their body is just a different body plan. But again, they're known only from Africa, the Tendaguru Formation, which we'll talk about at the very end of the class when we talk about individual dinosaur locations, and maybe possibly from the Morrison, from isolated material that's been kind of tentatively assigned to them. Again, when you find like scattered bones, it's really hard to say without the context of the full skeleton exactly what kind of dinosaur it was. So another relatively small ceratosaur is Noahosaurus. So Noah, so obviously Saurus is lizard. So what's Noah? Noah is the normal abbreviation, so noroeste, northwest, and A is Argentina, so it means northwest Argentina lizard. And you see that this thing is very small. It was originally grouped in with the quote-unquote raptors. We'll talk about them a little bit later. Raptors isn't really a group, but it's kind of how we would think of these things. You see here's a regular old house cat for scale, so even smaller than Alephrosaurus. So a very small ceratosaur. Again, if you look at least this reconstruction here of the skull, but again, you see how little material they're working with here. There are other specimens, but you're trying to build a dinosaur back from an isolated fragment of the skull, a couple ribs, some leg bones, and just like trying to fill in all the gaps and all the pieces. And so it's very tricky. But again, you use phylogenetic bracketing. You look at things that are more primitive, more basal. You look at things that are more derived, more advanced. To bracket in between, if features are seen here and features are seen here, it's probably in between as well. You look at other dinosaurs that have similar lifestyle, similar genetic, phylogeny, evolutionary history, and you use what you know about their morphology to kind of fill in the gaps here. So, and again, the less material you have, the less comfortable you are, the less confident you are, but it's not an impossible task. You can kind of build the whole story. So these are known from very isolated material. But one unique part about them is that they have a very unusual jaw and teeth. So if you look at the teeth here, they're much smaller than some of the other specimens that we've seen, and they also have a really strong kind of recurve. And the lower jaw is actually a little bit weird curve at the end here too. This has been interpreted to be an adaptation to piscivory, which is eating fish. So Pisces is the zodiac sign for fish. Piscivorous means eating fish. So they were also originally thought to have a sickle claw on their feet. So like in Jurassic Park, the big raptor claw that they kind of tap on the floor there for a dramatic effect. These were thought to have a sickle claw on the feet, that sickle killing claw. And so they would be like a similar lifestyle where they would kind of leap with the feet out front and kind of deliver that killing blow where they would try to actually like disembowel the victim with that big old sickle claw. It was actually later discovered that those claws were actually hand claws. And so that kind of changed the interpretation and kind of lumped them in with the ceratosaurs. Again, you don't see the prominent horn, at least on this reconstruction. But again, you do see that very kind of reduced arms. You see the arms getting kind of more and more reduced in all these specimens as we see them, as they get kind of farther up the chain of the ceratosaurs. But yeah, so that's Noahosaurus. And then the last kind of group of these is the Abelisaurids. So Abel is the discoverer, Abel's lizard, Abelosaurid. It's a group that shows kind of shorter snouts and much reduced arms. So you see here kind of the very kind of blunt, almost like a pug dog kind of smushed in kind of face here. Much reduced arms. You can't even see the arms on this specimen here. And you still see though that the characteristic head ornamentation, the horns. So their kind of defining characteristic is that they have these kind of taller, wider, shorter skulls. The skulls are more kind of compact and elongate, almost a little bit more like, you know, spherical almost, versus the very elongate skulls like we think of with like T-Rex or something like that. So that probably reflects a difference in their behaviors, a difference in what they're doing. So like T-Rex with those sharp banana-sized dagger teeth and that huge crushing bite force that we talked about in one of the homeworks, they're just kind of chomping out huge pieces of flesh and just gouging the food out, kind of like a crocodile would, where they're like grabbing and twisting and pulling and just chomping down on big pieces of flesh. Smaller ones are probably doing kind of like a bite and hold, kind of similar to like a lion, so, or the big cat. So big cats kind of tend to like overpower their prey. They'll try to get their mouths kind of around the muzzle and just kind of like suffocate the animal, or even around the throat and just kind of choke it out. You'll often see the big cats just kind of chomping on what they're just suffocating it. These probably hunted in a style a little bit more similar to how wolves do it. Larger wolves will occasionally do the takedown and the whole like bite and hold, muzzle, strangle kind of thing. But really they just kind of harass and grab and take little bites, inflicting kind of small wounds. Small, relatively small. Getting bit by a wolf is probably not a trivial experience, but they're not taking out massive chunks of flesh in most cases. They're just damaging the animal. They keep it on the run. They keep it moving until it just gets exhausted and kind of gives up. Kind of this death by 1,000 cuts model. No one of those bites is the fatality, but just accumulated with over time and the persistence and the exhaustion and the loss of blood and the fatigue. That's how they probably ended up hunting, because they didn't have the big crushing jaw like T-Rex to do that. They didn't have the size to do the kind of bite and hold on the larger dinosaurs. So it was probably more, again, like more similar to how wolves hunt. You also see in here that by this point in this line, the forelimbs are fully vestigial at this point. They don't really do anything. In fact, they're fused at the elbows. They're very limited mobility, pretty much useless for any tasks. Generally, so we talked a little bit about like the evolution of a wing. What good is half a wing? That's better than no wing. You can do a little bit of gliding with half a wing. What good is this stubby little arm? The answer is probably really almost nothing. Some speculation that they would use it in like copulation, mating, or maybe for like maybe pinning down, but it had very little mobility, and so it probably wasn't really used for much of anything. And the bones are actually fused, so it had very limited range. The Abelisaurids themselves, their range and their lifestyle. So one thing to remember throughout this whole course, when we're talking about dinosaurs, dinosaurs is a massive group of animals that has a huge diversity in space and also in time. So when you say like dinosaurs, it's similar to saying like mammals. So when you say like what are dinosaurs like, it's the same thing as asking like what are mammals like. Well, mammals are like lions, mammals are like giraffes, mammals are like humans, mammals are like gorillas, mammals are like whales and dolphins. There's a huge range of what mammals are like. There's also a huge range of what dinosaurs are like. Mammals also live on all different continents, and they're adapted very differently to all of those different continents. There's also a lot of extinct mammals that are very different from the mammals that exist today. So like woolly mammoths, saber-toothed tigers, those don't exist. So when we think about mammals, we don't have that temptation to think of them as like this homogeneous thing where all mammals that ever existed exist now, and they all live in the same place at the same time. So remember that dinosaurs are very similar. Dinosaurs are restricted to geographic areas. Some of them are more cosmopolitan, more global than others, especially when the continents are more assembled. But by the time we get to the late Cretaceous, when the Abelisaurids are present, the continents are very fragmented. So Pangaea, at the beginning of the Mesozoic, when all the continents were together, dinosaurs could very freely move from continent to continent. And so most dinosaurs that were around, so like Coelophysis, for example, was found on all the continents. There were no barriers or very few geographic barriers. At the end of the Triassic, we start rifting, well, I guess in the Triassic, we start rifting Pangaea apart. We start making like the Newark Basin, dropping down where they left their little footy prints in the sediment there. North America started separating away. So North America broke off from Africa, started separating from Europe. We started opening the Atlantic Ocean in the North Atlantic Ocean. The South Atlantic Ocean started opening a little bit later, separating South America from Africa. India, Madagascar broke off. Australia and Antarctica broke off as well. Eventually, Australia breaks off from Antarctica and drifts as its own little island. India drifts north and smashes into Asia to make the Himalayan mountains. But at this time and place, this is kind of the first time in a long time, the first time in the history of dinosaur evolution, where now instead of one massive continent, we have very distinct continents. And so on each different continent, different dinosaur fauna adapted to that particular environment, and the particular fauna, the particular ecosystem of that continent kind of develop. Another thing is that you see not only are the continents moving apart, but sea level is very high. There are no glaciers at this time locking water up on land. So all the water on Earth is in the oceans. It's not locked up in Antarctic ice sheet. It's not locked up in Greenland ice sheet. It's all melted into the oceans, as we're kind of heading for with the modern climate change. So sea levels are higher, and you see that cutting right through North America here is this Cretaceous interior seaway that actually divides North America in half to Appalachia and Laramidia. So dinosaurs are actually sort of different on both sides of this. So these Abelisaurids, they're very much dominant in the southern continents, so particularly South America, probably Australia and Antarctica, though there's not as much evidence of that. There's very little dinosaur material from there. Definitely India and Madagascar, we'll talk about some of those specimens, and maybe a little bit from Africa and maybe some isolated things from Europe. But by the time we get to the Cretaceous, these ceratosaurs are gone from North America. They're not there anymore. So what happened? Well, the carnosaurs and the coelosaurs, so we'll talk about those next couple days, they have become the dominant carnivorous dinosaurs in North America, in Asia. These things were just outcompeted. So these are a little, they just couldn't keep up with, for whatever reason, those other dinosaur groups were better adapted to those particular environments. We'll talk about how a little bit later, but so when we think of the ceratosaurs, by the time we get in the Cretaceous, they're really found on these southern continents and not so much on the northern continents. All the continents have kind of their own unique kind of dinosaur fauna. The northern continents are a little bit more similar to each other, and the southern continents are a little bit more similar to each other, but they're all kind of unique in their own little ways. Another thing that's sort of interesting is that Abelosaurid's range coincided with the range of the very large herbivorous titanosaurs. So a lot of the really large titanosaurs come out of South America, like Giraffotitan, Patagotitan, those massive sauropod herbivore dinosaurs. These things, the ceratosaurs, were around, and they were the dominant apex predators in these areas, and so they were hunting those, again, probably through that death by 1,000 cuts strategy. They weren't as beefy as something like a T-Rex or an Allosaurus, and so they had to work a little bit harder to take that down. But we start seeing these things really get kind of bigger, and they start kind of getting closer to that niche. So Abelisaurus, here's a human for scale. You see that, you know, this thing is significantly larger than the others that we've looked at. It's named after the discoverer of the type specimen Abel, so Abel's lizard. Unlike the later genre, there's kind of no true horns here. So we don't see the nose horn, we don't see any horns behind here, but there were kind of ridges on the snout and kind of above the eyes that might have supported like a keratinous or maybe even like a fleshy crest. So that's like softer material that wouldn't necessarily be preserved. Again, that's one of the problems with the fossil record is we only have the hard parts, we only have the skeleton. Looking only at the skull here, we don't see a lot of evidence for a crest, but there probably was a subdued crest at least. But these are the apex predators of their ecosystem. Very large, very imposing, very dominant carnivore. They were not competing directly with the larger carnivorous dinosaurs because they weren't present on the southern continents, or at least not to this degree. You also see in the larger bipedal dinosaurs, you also see these larger openings in the skull. Again, people are kind of tempted to put the eyes in here. So like you would put the eye like here where the laser pointer is. That's not the eye opening, that's the sinus opening. The eye is back here. Why do they have these big windows into the skull? Well, you see, it's a bipedal animal. You want the center of gravity above the hip. If you've got this massive skull hanging way out here on the end of this long neck, if it's entirely bone, big platy heavy bone, the animal's going to get front heavy and tend to kind of tip over. They do have this long, very muscular, probably fatty as well, tail to kind of counterbalance, but it's going to need a huge tail to counterbalance the skull if it was solid bone. And so what we see is that as the skulls get larger to accommodate larger and larger teeth, to accommodate larger and larger prey, they start getting more and more windows in the skull to lighten it so that they're not kind of tipping over. And so this is an adaptation that we see in these. We'll also see it later in the other large theropod carnivores, but this is a very intimidating, very imposing animal, and it's very much the top predator in its ecosystem. If we go to India, Rajasaurus is the most prominent apex predator there. The name translates to king lizard, so Raja is like an Indian monarch. Tyrannosaurus rex would be a little bit mad at that, the tyrant king of North America. So obviously, like one thing that always comes up with these conversations is like, who would win, Rajasaurus versus Tyrannosaurus or something like that? The answer is that they wouldn't fight. They were separated on different continents and they didn't live together. They didn't occur together. Tyrannosaurus rex was dominating the North American continent as the apex predator over there in the western part of the United States. Rajasaurus was dominating the Indian subcontinent, that little floating island that was now drifting off on its own towards an impending collision with Asia and the rising of the Himalayan mountains. One thing cool about Rajasaurus here, you see this very prominent horn on the forehead. So it was interpreted as possibly for display, so sexual display, so like horns on a deer, or sparring, kind of knocking into each other, or just kind of like jousting a little bit. But the Lametta Formation, where these things are found, it also includes kind of large sauropod titanosaurs. So again, these Abelisaurids were found over the range of these large herbivorous titanosaurs. Those were the prey that they were after. And so this is why Rajasaurus got so large. But again, not large enough to kind of directly take this on and do like the bite and hold and chunking off large pieces of flesh. So it was probably like, again, a very kind of like canine hunting strategy versus like a big cat strategy or a crocodile strategy. Another interesting thing is that one of the proposed causes of you'll see KPG, K is for Cretaceous, even though it starts with a C. They use K because C is already used for Cambrian. So K is Cretaceous, PG is Paleogene. Sometimes you'll see KT, Cretaceous Tertiary. Tertiary is kind of an older name for Paleogene. So KT or KPG, this is the large extinction event that killed off all of the non-avian dinosaurs, all of the non-bird dinosaurs, and also a significant percentage of other life on Earth. One of the causes is the meteorite impact, the asteroid impact. Another potential cause that was happening even before that is there was this massive eruption in India of these Deccan traps. It's this massive kilometers thick lava flows that was erupting over the course of millions of years. And so Rajasaurus doesn't actually even make it to the Cretaceous Paleogene boundary. It dies off beforehand, and a lot of the Indian dinosaurs, most of the Indian dinosaurs, maybe all of the Indian dinosaurs, they don't make it all the way to the asteroid impact. They're dead before that even happens because they're in close proximity to this massive, kind of unprecedented, there's no modern equivalent of volcanism on this scale, eruption. So this it kickstarts climate change, it kickstarts a lot of different environmental catastrophes. And so when we get to KPG extinction or KT extinction, there's always this debate about, was it actually the asteroid that caused the extinction of dinosaurs? Because there's pretty good evidence, and Rajasaurus is one example, that they may have already been in decline before the asteroid even hit. And so the asteroid certainly didn't help, but it might not have been the cause. Generally what we see is that mass extinctions have multiple causes, kind of the Murder on the Orient Express, where everyone did it to some degree. There was a lot of variables, there were a lot of things that happened, and that none of them were good. To get such a large extinction event, you need a lot of things going wrong at the same time. So Rajasaurus and all the rest of the Indian dinosaur fauna, they didn't even make it that far. On other drifting portions of the continents, Majungasaurus, named after the Mahajanga in Madagascar, known only from Madagascar. So again, if we put the continents back together, South America, you see the outline here of Africa, Madagascar, India, Antarctica, and Australia are all sort of together. If we fast forward the clock here, we start opening up a gap between Africa and the other southern continents. India and Madagascar start floating away, start drifting away as a whole piece. But then later on, Madagascar rifts off of India. How do we know that? Well, you can actually see the fracture zones on the ocean floor that trace their movement. And you also see the puzzle pieces. You can actually put the coastlines back together. Madagascar fits snugly right into this little piece of India, and it also fits snugly right into the coastline of Africa. Again, one of the pieces that Alfred Wegener used to support his continental drift theory is that the continents move around because they kind of look like they fit back together, and they do. You can see again, South America fits nice and snugly right into this little hollow here in Africa, because that's where it came from. That's where they separated off from. And again, you can see the fracture zones going across the ocean. That's a telltale mark of where it's been. And so if you rewind the geologic clock, you can see what happened. So India at this time is free-floating, drifting on its own. Rajasaurus is dominant on that subcontinent. Majungasaurus is filling a very similar niche in Madagascar. So this is the dominant predator here in Madagascar. No competition from Tyrannosaurus rex. Tyrannosaurus rex is not around in this time and place. No competition from Rajasaurus. Rajasaurus is in India. So these are left to their own devices here in Madagascar, and they're the apex predator here. What you see is that one thing that's cool about them is that as they grow up, their skull shape and their eye sockets change dramatically. So there's a lot of material from Majungasaurus, enough to actually reconstruct a growth curve, enough to actually see how the animal changes throughout its growth. So again, like think about how a human changes its ratios and things over time during its ontogeny, during its growth. Dinosaurs did the same thing, except to a lesser extent. So remember, they were kind of already the same basic shape, and then they just grew up very quickly. Majungasaurus, though, the ratios changed a little bit, and so the juveniles were probably actually hunting entirely different things than the adults were, because they were adapted to different things. This is something that we see again repeated later on in the theropods, and we already talked about, like, why are there no kind of like medium range dinosaurs? They're all kind of like small or pretty large. This is possibly why the juveniles are filling that environmental niche. So there's also some evidence of possible cannibalism with these dinosaurs. Then there's the question of whether it was actually like actively killing or whether it was just scavenging on their remains. And they also replace their teeth at a very high rate, about once every 2 months or so. Both of these adaptations are probably responses to a fairly harsh environment where resources were pretty limited. If resources are pretty limited, you're going to scavenge whatever is available. And you're also going to, so there's pretty good evidence that these were eating or chewing on bones, trying to get to the marrow, and that wears out the teeth quicker, so they need to recharge their teeth battery quicker. They didn't have the kind of dentition and bite force of a T-Rex just crunch through bones. They had to kind of like saw at them, and that really is taxing on the teeth. A lot of these other dinosaurs actively avoided chewing on bones for that exact reason. It wears your teeth down. You don't want to be doing it very much. And so that's Majungasaurus. And the last one that we're going to talk about, Carnotaurus, is probably the most famous ceratosaur. It translates to, so carno, like carnivore, meat eating. Taurus is bull, again, like think about the horoscope sign, Taurus. So Carnotaurus means meat-eating bull. After its thick bony horns above its eyes, it literally has bull horns. What were those horns used for? Again, when there's something, a structure that doesn't have like an apparent use, that doesn't really fit with that like form follows function, one of the usual interpretations is that it's sexual display. So like, why do peacocks have those massive feather fan tails that are an evolutionary disadvantage? At least from an escaping predator's standpoint, why do they have those? Sexual display. Why do they have these horns? Perhaps for sexual display, jousting with rivals, or maybe just some gentle sparring. But these things are very large in size, and there's no evidence that they've had feathers. So a lot of these, again, the larger dinosaurs, the evidence for feathers is pretty sparse. So again, like we wouldn't really expect necessarily a larger dinosaur to need feathers, because they're just retaining their heat based on size alone. They don't need the insulation. They have that high thermal inertia. So Carnotaurus, the very large ceratosaur, probably didn't have any feathers, or there's no evidence at least. But remember also that absence of evidence is not evidence of absence. Just because we don't see feathers and they're not recorded doesn't mean they didn't exist. We just haven't found them yet, or they actually didn't exist. Another thing that's really unique about Carnotaurus is that the forelimbs, the arms, are dramatically reduced. You can see that they're comically reduced. they're useless. So we often poke fun at T-Rex for its short little stubby arms. Compared to Carnotaurus, T-Rex has beautiful, delicate, elongate arms. Because it was kind of so well balanced, it was probably pretty fast, but it has a relatively small brain. And so what we see is that in these ceratosaurs, they are carnivorous dinosaurs. Where they overlap with some of the more derived, more advanced carnivorous dinosaurs, they tend to get out-competed, probably from like a morphology, like size and musculature and adaptation standpoint. They're probably on about equal footing, but really the brain is the big difference. These things have a much smaller brain size relative to their body size than some of the later theropods like T-Rex. We talked a lot about T-Rex's brain and how well developed the sight was, how well developed the hearing was, how well developed the smell was. These were a little bit more limited in those capacities, and that's probably why they were kind of limited to the southern continents, where those dinosaurs were a little bit less prominent, or in most cases entirely not there. So that's all we got for today. Hope you enjoyed that. Hope you're keeping up in the class. If you have any questions, make sure you reach out. That's all I got, and goodbye.